All right, welcome to the Explainer. Today, we're going to tackle a really powerful idea. How do you make the best possible guess when you just don't have all the facts? We're talking about a tool that starts with some pretty simple logic, but, and this is the cool part, ends up unlocking the actual laws of physics. Okay, so here's the game plan. First, we're going to frame the problem with something we'll call a best guess machine. Then we'll get into the key concept, entropy, and see how this whole thing works. And then we'll get to the payoff, how this one idea has huge implications, everywhere from physics to information theory. All right, let's kick things off with a simple puzzle. But this puzzle, it really gets to the heart of a really deep problem, which is, how do you make an honest guess when you only have a tiny piece of the picture? So picture this. Someone walks up to you, hands you a die, and just says, hey, this thing's loaded. And that's it. That's all the info you get. Now, what's your best guess for the probability of rolling a 6? What can you even say? Any answer you give just feels like a total shot in the dark, right? Okay, a fair die, that's simple. We all know it's a 1 in 6 chance for each side. But what if I give you just one piece of extra information about our loaded die? Let's say we know that the average roll over many throws is 4.5. Now, all of a sudden, we know something. The big question is, how do we take that one little fact and use it to figure out the most honest, unbiased probability for every single side of the die? Well, that is the exact problem that the principle of maximum entropy is designed to solve. So at its heart, MaxEnt is basically this best guess machine we've been talking about. It's a formal way of assigning probabilities that, and this is key, reflects exactly what you know and absolutely nothing more. You're not adding any of your own biases. It's just the most conservative, most honest guess you could possibly make. Okay, so to really get how this machine works, we've got to talk about a word I'm sure you've heard before, entropy. But we need to look at it in a totally different way. So whatever you think you know about entropy and, messy rooms or disorder, just for a second, set that aside. Let's think about it in terms of pure information. First up, we have this wonderfully intuitive idea called surprisal. And really, it's exactly what it sounds like. You flip a coin, it lands on heads. Not very surprising, right? So low surprisal. You win the lottery? That has an incredibly high surprisal value. It's basically just a mathy way of saying, whoa, I did not see that coming. So, if that's surprisal, then what's entropy? Well, entropy is just the average surprisal across all the possible things that could happen. Think about our fair die. Every outcome is equally likely, so they all have the same surprise. The average is easy. For our loaded die, things get a bit more complicated, sure, but the core idea is exactly the same. Okay, so here's the absolute crucial point. The principle of maximum entropy says that our best guess, the most honest one, is the probability distribution that has the highest entropy. Now, what does that mean? It means we're looking for the set of probabilities that is, on average, the least surprising. It's the flattest, most spread out distribution possible that still fits the facts we know. We're maximizing our uncertainty, which means we're not baking in any extra assumptions we can't justify. Okay, so how does this all come together? Let's look at the actual process. How does this machine take the few facts we have and actually spit out the best possible guess? It's basically a 4-step recipe. First, you start with maximum uncertainty. You assume you know nothing, so every outcome is equally likely, a flat line. Second, you introduce your constraints. These are the hard facts you do know. For our die, the big constraint is that the average roll has to be 4.5. Third, you tune the probabilities. You gently tweak that flat line just enough to make it match your constraint. And fourth, bam, the result is the most unbiased, most honest probability distribution that fits your data. Now, you might be wondering what's doing this tuning in the background. Well, the engine under the hood is a pretty clever mathematical tool called Lagrange multipliers. And look, you don't need to get bogged down in the math. Just think of them as precision dials on a machine. The machine turns these dials, carefully nudging the probabilities just enough to honor our known facts, like the average being 4.5. But it does it without accidentally sneaking in any extra assumptions we didn't ask for. Okay, I know this might all sound a little abstract, maybe like just a neat trick for statisticians, but here's where it gets mind-blowing. When this exact method of reasoning was applied to physics back in the 1950s by a physicist named E.T. Jaynes, it caused an absolute revolution. What Jaynes figured out was, well, it was just astounding. He showed that the laws of thermodynamics, these fundamental rules of the universe, they aren't arbitrary. Not at all. They are the inevitable result of running our best guess machine. Think about that. If you feed the machine just one single fact, that the average energy in a closed system is constant, it automatically derives the entire framework of thermodynamics, just as the most honest guess possible. And this table here illustrates it perfectly. In physics, they call these different scenarios ensembles, but don't worry about the jargon. Just think of them as our best guess machine running with slightly different starting info. If you tell it the total energy is perfectly fixed, you get one set of rules. If you tell it you only know the average energy, you get another set of rules and a whole new set of concepts like temperature. It's the exact same logic every time, just with different constraints. And this is where it gets really, really profound. Remember those mathematical dials we talked about, the Lagrange multipliers? The ones the machine uses to enforce the energy constraint? Well, it turns out that dial isn't just some abstract piece of math. It literally is temperature. Or to be precise, it's 1 divided by temperature. This machine, running on nothing but pure logic, naturally discovers one of the most fundamental quantities in all of physics. That's just incredible. The real power here is that this isn't just philosophy. It makes predictions you can actually go out and test. Now, this equation might look a bit intimidating, but what it's saying is actually beautifully simple. On the left side, you've got a term that represents the tiny, random fluctuations in a system's energy, the jiggling of atoms. And on the right, you have something we can easily measure in a lab, its heat capacity. So this machine, built on pure reason, predicts a direct, measurable link between the invisible world of atoms and the world we can see and touch. It's a stunning prediction, and it comes right out of this simple principle of making an honest guess. But here's the thing. This best guess machine, it isn't just for physics, not by a long shot. Its core logic is totally universal. It applies literally anywhere you have to make a decision or a judgment with incomplete information. The math behind this core idea, shows up everywhere. We see it in communications theory, helping measure how much information is shared between two signals. We see it in quantum mechanics, quantifying things like entanglement. Even in ecology, scientists use a version of this to figure out which model best explains a complex ecosystem. The one that fits the data with the fewest extra assumptions. From the cosmos down to computer science, it's the same fundamental logic of the best guess machine, over and over again.
So, let's bring it all home. What's the big takeaway here? Why does this all matter?
Because the principle of maximum entropy is way more than just a clever tool. It's a universal, rigorous framework for how to reason when you're faced with uncertainty. It shows us that something as fundamental as the laws of thermodynamics, they aren't just laws of physics. At their deepest level, they're laws of information. And that leaves us with a pretty provocative thought to chew on. If the laws of thermodynamics can be derived simply as the best guess given a single, simple constraint, well, what other laws of nature are out there just waiting to be found the same way? What happens if we find the right constraint and just turn the crank on our best guess machine one more time?